Alright, today we're going to look at Unit A, Day 3, complex fractions, or complex rational expressions. I think it's fairly straightforward. Should be a little bit easier than yesterday. The fractions look a lot worse, but they're not that tough to get through. So I made a little list up top of the steps that you'll want to go through. So if I go too fast through them, you'll want to pause and get them written down. I will read those hieroglyphics for you. So step 1 is to find a LCD, and this would be an LCD for all the little fractions in these problems. So what I mean by that, not a very mathematical term, but these little highlights down here on example 1, we're going to find the LCD for that. Then we're going to multiply numerator and denominator by the LCD. What this will actually do is get rid of those little fractions. It'll reduce out the little fractions, and we'll be left with kind of one big denominator and one big numerator. Then we'll take those two things and we'll factor and reduce. As a side note, the restrictions become a little more complicated. We need to find the restrictions for each of the smaller denominators, and then we're going to need to find restrictions for the whole original denominator. So there's a little bit more to do on restrictions. But let's go ahead and get started. For some reason, when this went over to PDF, a lot of these subtractions didn't get transferred over, so I'm going to have to write some of those in. When we look at this first example, we see for the LCD, the unique factor is x. The highest exponent there is x squared, so the LCD is going to be x squared. So what I'm going to do is I'm going to multiply top and bottom by x squared. So the numerator gets multiplied by x squared, and the denominator gets multiplied by x squared. And then what we're going to find is that as I distribute this, in our first, in the top, we get x squared over x. I'll write it down, but in the future I probably won't. Plus x squared over x squared. All of this is over the distribution in the bottom, x squared over x squared minus x squared. And then we're going to reduce all these. So x squared over x becomes x plus 1. X squared over x squared becomes 1 minus x squared. And although this denominator is not in the order we're used to, it is still a difference of squares, so we're going to put a dotted line here. Maybe we'll need it. We're going to factor this to 1 minus x squared and 1 plus x squared. So we have x plus 1 on top. The bottom is 1 minus x. I think I might have said that wrong, sorry. 1 plus x. Unlike subtraction, addition can be in any order to reduce. So x plus 1 and 1 plus x both reduce. And we're left with 1 over 1 minus x. In terms of restrictions, we know that x cannot be 0 from the original expression we know down here, x cannot be 1. But we've got one little hidden thing, may not be as obvious. If we come back here and look at the original denominator, there's actually one other number that makes this denominator 0. The way that you can solve this is, let me use red here, is just set this thing equal to 0. So we need to know when 1 over x squared minus 1 equals 0. I would multiply every term by x squared, and you actually get 1 minus x squared equals 0. So 1 plus x and 1 minus x equals 0. And hopefully at this point you can see that x is 1 or negative 1, which, since we're finding restrictions back in our original problem, we're going to say x it cannot be 1, and x cannot be -1. So we found that little third restriction there. Okay, so restrictions and answer. All right, let's look at example 2. So here our LCD is the unique factors of the denominators. So we have a factor of x and we have a factor of 5. So our LCD is 5x. I'm going to multiply top and bottom by 5x. When I distribute this, things are going to reduce. All the denominators will reduce out. So 1 over x times 5x, the x's will reduce, leaving 5. 1 over 5 times 5x, the 5's will reduce, leaving x. 5x times 1 on the denominator is 5x. And 5 over x times 5x, the x's will reduce, and this leaves us with 25. The denominator will reduce. We get 5 plus x over 5 times x plus 5. Now, be careful. Subtraction, we need to have the exact same order or factor out a -1. But with addition, we don't need to change the order. You could if it made you feel better. But commutative property addition says as long as it's positive addition, we can do it in any order we want. Those two reduce out. We're left with 1 over 5. We still have some restrictions on x. So we know from up here, let me use a little red highlighter. So here we know x cannot be 0, same thing down here, but we also need to know when that whole denominator becomes 0. So we're going to say 1 plus 5 over x equals 0. If I multiply both sides by by x times x times x, I distribute that, I'm left with x plus 5 equals 0. So x cannot be -5 either. So for my restrictions, we've got x cannot be 0 or -5. If you want to put those in solution set form, you can, or bracket form. That's okay. Sorry, it went a little fast. If you need to go ahead and pause this so you can get it written down, go ahead and pause now. I'm going to go on to the third example. Alright, so we're missing our minus here. This is the exact same thing. Sorry about that. So there is another way to do these. You could get, instead of getting rid of all the denominators, which I prefer, you could write these as one big fraction over one big fraction, and then instead of divide, multiply by the reciprocal. So to do that, you would say the LCD for the top is x squared. The LCD for the bottom is x squared. And then I think to myself, what do I need to get x squareds? Well, I need x over x for this one. I need x squared over x squared here. And this will then become x over x squared plus 1 over x squared all over 1 over x squared minus x squared over x squared. These won't always have the same, the numerator as a fraction won't always have the same denominator as the denominator as a fraction. But I'm going to write these as one big fraction, so I'm going to start over here. We get x plus 1 all over x squared for the numerator. We get 1 minus x squared all over x squared for the denominator. There's one, you could handle this a unique way, but I I think let's go ahead and do this as we normally would. So dividing by the denominator is going to be the same as multiplying by the reciprocal. So instead of dividing by the yellow highlight, I'm going to write the numerator. I'm going to multiply by its reciprocal, or the flip. So now what we're going to see is the x squareds reduce, and we are left with x plus 1 over 1 minus x squared, and I think you'll see that that will reduce. So this comes out to be what we had before. Factor the bottom to x plus 1 plus x, 1 minus x, and this will reduce to 1 over 1 minus x, and we'll have the same restrictions as we did in example 1. This really isn't my favorite way of doing it. It seems to be more work, in my opinion. But it might be a little bit more familiar, the processes. I'm going to stick with the first method. If you like this second method and you need more examples like that, why don't you come by sometime before or after school, and I'll be happy to expand on it a little bit more. If you need to pause, go ahead and pause. I'm going to go on to example 4. Again, example 3 was just a repeat of example 1, so didn't miss much. All right, let's see if we can zoom in. My copy is missing this minus here and this minus here. Okay, so looking at this, we're going to find the LCD for all the little fractions. So here we've got a denominator, here we've got a denominator. So my LCD is going to be the unique factors of the denominator, which is going to be x minus 2 times x plus 2. It's good to see it in factored form. It's also might be helpful to see it in expanded form. So x minus 2 times x plus 2 is our difference of squares, especially this one. It's much shorter to write it in expanded form. But what we're going to do is we're going to take this LCD and we're going to multiply top and bottom by it. So sometimes you'll see me write it as the expanded form. So I'm going to multiply the top by x minus 2 times x plus 2. I'm going to multiply the bottom times x minus 2, x minus 2 times x plus 2. Again, we talked about this yesterday, but just to be clear, this thing that I'm boxing in the yellow highlight, this equals 1. So I'm not changing any values. I'm multiplying that whole original fraction by 1. So the value of it is still the same. Now I'm going to distribute, so the x minus 2x plus 2 goes to both terms in the top. It goes to both terms in the bottom. And I'll write it out again, although I don't normally always write it out. So this is going to equal, let me get our LCD out of the way. Yeah. All right, get out of town. This is going to equal times 1 is x minus 2 times x plus 2. Normally I'd just write x squared minus 4. Minus, and then when we distribute to the second, we're going to find these x minus 2's will reduce. It's okay to write it. Just write the reduction first. I want everybody to see what's going on. And then the whole bottom is going to be, again, 1 times is x minus 2, x plus 2, plus 5 times x minus 2, x plus 2, all over x minus 2. And this video is about to end, but we're going to see the reduction real quick. The x minus 2's reduce here. The x minus 2's reduce. Sorry, that should be plus, shouldn't it? The x plus 2's will reduce. And I'll see you on the next video.